here, and we're looking at applying parametric equations with motion. So we have previously, in prior units, we have looked at how we can write the initial velocity of an object that's being shot, launched, thrown, how we can write it in terms of its horizontal and vertical component. So imagine we have our initial velocity given to us, and we know the angle at which it's being launched. We have learned that this can be written as the initial velocity multiplied by the cosine of the angle, and then the initial velocity multiplied by the sine of the angle, where the first piece represents the horizontal component, and the second piece represents the vertical. Okay, so the moment it is launched, we are able to utilize this to examine the velocity in the horizontal movement and the vertical movement at the beginning. So let's just have a quick visual of what is going on here. So let's say that we are launching something and we are above the ground a little bit. So this is our initial height, y sub 0, and that we have its velocity, v sub 0, given to us, as well as the angle at which it is launched. Okay, we can take that and write it as components, where we have the horizontal component of this velocity, which would be v sub 0 cosine of theta, and we have the vertical component, which would be v sub 0 sine of theta. All right. So during the path of this object, so as this object is moving through the air, so we understand it's going to be a parabola with our understanding of motion of objects. The vertical component, this changes. Use black. This changes during the flight due to gravity. Okay, so whatever the vertical velocity is at the beginning, it will be different by the end, or even by like a second later. The vertical velocity is changing throughout the flight of the object. Whereas the horizontal component, this is constant throughout flight. So we are today, in this lesson, we're going to look at how can we utilize parametric equations to really talk more about projectile motion. So focusing on velocity, if we wanted to talk about the velocity of an object as it's flying, because the velocity is constant in the horizontal direction, in the x direction, because of that, whatever the velocity is at the beginning in the horizontal direction, it remains that the whole way through. So at every point in time throughout its flight, the velocity will always be the initial velocity multiplied by cosine of theta, always. Okay, whether it be 2 seconds into the flight, whether it be right before it lands, the horizontal velocity will always be initial times cosine of theta. Whereas, as I said up here, the vertical changes due to gravity. So we have two different formulas, and I'll explain why there are two different ones. There's negative 32t plus v sub 0 sine of theta. So there's our vertical component, and here's the piece that's changing it. Or we have negative 9.8t plus v sub 0 times sine of theta. So the difference, if you have not been exposed to any sort of physics course yet, negative 32, this is the acceleration due to gravity. Now this is negative 32 is the acceleration due to gravity when you are measuring in feet. So when your measurements are taken in feet, when your speed is given in feet, then we are going to be using negative 32t. Whereas negative 9.8, this is the measurement, the number we're going to use when we measure in meters. All right. So we just recognize, what are the measurements taken in, and we utilize the correct equation. Okay. But both have our vertical component added on to it. So these two we can use when we examine velocity. So what if we don't want to examine velocity? What if we want to know, how far did the object go? Or what was the highest point in the object's flight? Well, there we're going to have to look at the displacement of the object, so x and y. Now, both of these equations are going to be in terms of t with respect to time, hence how we can use parametric equations, because both of these equations are going to be written in terms of t. So to get the horizontal displacement, to know how far the object is moving horizontally, we are going to take its velocity in the horizontal direction, so initial velocity times cosine of theta. We're going to multiply that by the time we desire. So we want to know how far we are away after 3 seconds. Well, I multiplied the horizontal component by 3, and I have it. All right. So this is the horizontal distance from the initial position. You should understand that. So then for the y component, to know our vertical movement, we have, again, because of units of measure, we have two different formula. For in feet, we have negative 16t squared plus v initial sine of theta t, parentheses, plus our initial height. All right. And then the other version, if we're measuring in meters, would be negative 4. There you go. Negative 4.9 t squared plus, and the rest is the same. Okay. So I'm gonna write this down. One is for when measured in feet. The other is for when measured in meters. Okay. So these two equations will help us examine the displacement, whether vertically or horizontally. So we need to know these formula. We need to know these 4 equations. The two parametric equations that we see, we need to know them. So let's look at 2 examples. So let's say we have papers. There we go. Okay, so Kevin hits a baseball 3 feet above the ground. So right here we have an initial height with an initial velocity of 150 feet per second. So we have our v sub 0 at an angle of 18 degrees. So here's our theta. So I'm going through, as I'm doing this, as I'm reading it, I'm marking what I have. So we have that. We have 3 items. Will the ball clear a 200-foot wall that is 400 feet away? Okay, so having maybe no exposure to parametric equations and possibly even projectile motion, how do we work with this? Okay, how do we work with this? Let's think of a game plan. We're dealing with displacement. So our equation, our question doesn't focus on velocity. So it tells us we're going to be using our displacement equations. So we have x equals, so it was initial velocity times cosine, so 150 times cosine of theta multiplied by time. Okay. Our vertical equation was, since we're dealing with feet, it's going to be negative 16 t squared plus vertical velocity, initial velocity sine of theta times t, and then plus our initial height, plus 3. Okay, so just using the equations we saw just a moment ago. So what time, so will the ball clear a 20-foot wall that is 400 feet away? So we're asking, when we were 400 feet out, is the vertical height going to be above 20 feet? Well, the question is, well, first of all, we don't have a time. When will the ball reach 400 feet? So let's write this down. So what time t will it take to reach 400 feet from Kevin? So this is a horizontal distance. Understand that. This is a horizontal distance, meaning we're wanting to know when will this equal 400. Okay. So we have an equation that we can just solve. So if we were to divide the two here, let me clear what we have. So if we were to solve this, 400, we divide this by, let's get our fraction bar. There we go. Let's say I want to do 400 and we want to divide that by 150, cosine of 18. We are in degree, good, so we hit enter. And we see that our time is approximately 2.8039 seconds. So we have that. We have our time. This is the time to reach 400 feet. Now, that's good for us. We use one equation to get the time. Now, with this time, we will find out whether or not at 2.8039 seconds, are we above 20 feet? Because if we are above 20 feet at this time, then it's going to clear the wall. So we want to know, now at this point, let's write this down. So now is the vertical height at this time above 20 feet. So it's a matter of, let's place our time into our equation. So negative 16, 2.8039 squared. It's going to be a long expression. Let's write this down. Plus 3. Okay, I had to put my plus 3 down below. So typing this into the calculator, we find, let's see. Okay, so negative 16. Plus. We get approximately 7.1782 feet. So to answer our equation, to answer our question, will the ball clear the wall? No, because it's less than 20. So the ball does not clear the wall. So before we move on to the last example, I just want to go over the process we went through. We noticed that we were not dealing with velocity. So therefore we wrote our displacement equations, both our horizontal and vertical. So we were wanting to know, first thing, because the wall is at 400 feet, how long will it take to reach 400 feet? And that was a horizontal displacement. We can put this. This is a horizontal displacement. So we set this equal to our horizontal equation. Got our time. We used one equation to get a time, and then with that time, plugged it into the other equation. This is very common, I can tell you that. Using one equation to get something, and then using that value with the other equation to get the actual answer we desire. So we had our time, we plugged our time into the vertical component to see if we did in fact reach above 20 feet at that moment, and we did not, so the ball does not clear the wall. So let's try this process again. So I'm going to block this out. First part, and then second part. found the time, and with the time, found a vertical distance. So what do we have to end with? So Nancy, gotta love this name Nancy. Nancy hits golf balls off the practice tee with an initial velocity. Okay, so let's mark our text. 180 feet per second, so this is our initial velocity, with her driver club. How far down the fairway, so that's how far down the fairway, that seems like a horizontal displacement. Okay, that we desire. Does the ball hit the ground if it comes off the club making a 20-degree angle? So there's our theta with the horizontal. All right, so thinking of this, we're actually given a little bit less information than we had before. We desire the horizontal distance to land, so that's what we desire. So we're not dealing with velocity, nothing's telling us to work with velocity. So we're, again, using the displacement equations. So initial velocity times cosine of our angle, multiplied by time. And then our vertical component would be dealing with feet, so negative 32. That's not true. That is not correct, is it? That's not correct, Mr. Beal. Sorry, guys. Negative 8, nope. Negative 16, there we go. Negative 16 t squared plus 180 would be sine of 20 times t. And thinking of what our initial height is, well, we're hitting off of a t, so we can assume that the vertical height is so small that our vertical height at the beginning is 0. Again, because it's rather small compared to what it's going to end up being throughout the path. Okay, so we desire how far down the path we desire this x. We need to know first, let's write this down, we need to first find the time. How long will it take to land? This is time. How long will it take to land on the fairway? So believe it or not, we cannot use our horizontal to figure this out. So we're wanting to know how long will it take to land. Well, to land, that fairway is one word, I guess, there we go. We're wanting to know when is our vertical height 0. When is our vertical height 0? So we're going to set our vertical equation equal to 0. Okay. And we're going to solve for a time, and with the time, we're going to plug it back into our horizontal equation. So let's work with this. So let's see. So we're wanting to solve this equation, so we're just using algebra skills. Both terms have a t, so we can factor a t from each, giving us negative 16t plus 180 sine of 20. Okay, so in solving this, we get t to equal 0, which makes sense. It's a height of 0 at the beginning. And then we want to have t, negative 16t plus 180 sine 20 equal to 0. I'm just using the idea of I have two factors equaling 0. I set each factor equal to 0. Okay, just larger numbers. So we solve this problem. So we would have negative 16t equals negative 180 sine of 20 divided by negative 16. And when we do that, I went ahead and performed the calculation ahead of time. We get 3.8477 seconds. This is to land, by the way. To land, it takes 3.8477 seconds. Now we can figure out, with that time, what is our horizontal displacement. So this is all part 1 to the problem. So part 2 will be taking our horizontal equation and multiplying it by the time. And when we perform that calculation, we get approximately, and you can do this as well with me just to check it, but we get approximately 650.8180 feet. Now we'll add onto this down the fairway. This is our horizontal distance. Okay, so recapping, very similar strategy as before. We used one equation to get a time, and with that time we substituted it into the other equation. That is a very common strategy when dealing with projectile motion. Use one equation to get a time, use that time for the other equation. Here we were looking at, we desired a height of 0 because that's when the object will land, that's its height when it lands. So we wanted the time for when it lands. We got 0, that makes sense because that's at the very beginning, it's height of 0. So we had this other part that we solved for. So it took this long for the ball to land. So then with that time to land, we placed that time back into our horizontal distance that gave us the distance from the tee that the ball went. So really utilize the strategy. Mark your text up with what you're given. Most often we'll be using our displacement equations, x equals y equals, and then utilize the strategy, get a time using one equation and use the time with the other. All right, so good luck guys practicing this. Take your time, really go through the steps, use those strategies that I shared with you, and I'll see you in the next lesson.